Welcome to The Explainer. I am absolutely thrilled you're tuning in today because we're going to unpack something that is just fascinating. We constantly talk about lines of code, but have you ever wondered what actually powers the digital magic we rely on every single day? It's not just the code itself. There is this hidden, underlying mathematical engine running beneath the surface of our entire modern digital lives. And today, we are shining a huge spotlight on it. We're exploring the incredible world of discrete structures. And hey, I know that sounds like dry academic theory, but trust me, it's not. This is the literal bedrock of computer science, artificial intelligence, and global networks. So let's get right into it. Okay, let's kick things off with a question we've all probably muttered to ourselves while sitting in bumper-to-bumper traffic. How does your GPS actually know the fastest route in real time? Or, for that matter, how does ChatGPT process your weird, specific prompts to generate incredibly human-like responses in just seconds? We totally take these everyday tech marvels for granted. But behind the scenes, there is a very specific type of logic at work, constantly calculating, constantly optimizing. And if we want to understand how it pulls that off, we have to understand the language it speaks. And that language is discrete structures. At its core, this is the mathematical foundation for processing finite, distinct data. Think about it like this. The real world we live in is continuous, it's messy, it's chaotic. But computation? Computation requires separate, highly distinct values, like zeros and ones. Discrete structures provide the exact mathematical framework computers need to translate all that real-world chaos into actionable, bite-sized data. It's the only way they can actually do something useful with the information we feed them. If you map all these concepts out, it's basically the ultimate mathematical blueprint of computer science, and it all ties together so brilliantly. It starts right at the foundation with basic rules of logic and modular arithmetic, but then it branches out. It takes that logic and applies it to map inputs to outputs, which leads us to graph theory, the study of networks and paths. Take it a step further, and you get these specialized graphs called trees that handle hierarchies and searching. And running alongside all of that are advanced algebraic structures dealing with security and data compression. It's this massive, interconnected web where unlocking one mathematical concept just leads you straight into the next, powering real-world applications like cryptography and network flow. To really appreciate the power of this, we're going to travel back in time for a second. The year is 1736, and we are in the city of Königsberg. This city had a really unique layout. It featured two large islands connected to each other and to the mainland by exactly 7 bridges. And the citizens of Königsberg were absolutely obsessed with this massive, seemingly impossible puzzle about those bridges. Here's the challenge they faced, and I want you to mentally try to solve this right now as we're talking. Can you cross every single bridge in Königsberg exactly once without retracing your steps and without crossing the same bridge twice? Imagine you're drawing the route without ever lifting your pen from the paper. People literally walked the city for years trying to figure out a path, but they always ended up stuck, or they'd miss a bridge. It became this legendary, infuriating problem. Enter the brilliant mathematician Leonhard Euler. The crucial thing here is how Euler looked at the problem. First, he proved that the puzzle was actually impossible to solve physically. But his true genius wasn't just, ruining everyone's fun. It was how he framed the whole situation. Euler realized that the physical distances, the size of the islands, the length of the bridges, none of that mattered at all. He stripped away the physical map entirely. He represented the places as vertices or nodes, and he represented the bridges simply as edges connecting them. By focusing purely on those connections, Euler basically gave birth to graph theory on the spot. And that is the exact mathematical framework used by modern routing today. Fast forward to right now, and Euler's historical breakthrough is sitting right there in your smartphone. That abstract concept of vertices and edges, that's what powers Google Maps and Uber. They use shortest path algorithms, like Dijkstra's algorithm, to navigate through heavy traffic in real time. It's exactly how social media platforms recommend friends or analyze influencers. In that scenario, you are a vertex, and your friendships are the edges. It's the absolute backbone of network routing in cloud computing, and it's even heavily used in generative AI for reasoning and mapping out complex knowledge. So yeah, a bridge puzzle from 1736 literally paved the way for the entire 21st century digital autonomy. Crazy, right? But we have to ask, what happens when we misunderstand these complex graphs? Well, the consequences can be downright catastrophic. Let's look at the 2003 Northeast blackout across the United States and Canada. It started out simply enough, just a localized fault in a power grid. But because of failures in monitoring and connectivity analysis, this tiny local problem went totally undetected. The error rapidly cascaded through the interconnected transmission lines. And the result? Over 50 million people lost electricity. It caused billions of dollars in economic losses and completely paralyzed healthcare, transportation, and communication systems. It really highlights the stark contrast in how we view critical systems. Physically, when you look at a grid, you see concrete power stations, substations, big, heavy transmission wires. But mathematically, engineers have to view this entirely differently. To them, that grid is a massive, highly sensitive graph of dependent vertices and edges. If you fail to properly analyze the mathematics of those connections, if you don't account for how a failure at one vertex is going to impact its connected edges, a single highly localized glitch can bring down an entire international network. Understanding discrete structures isn't just academic. It is quite literally a matter of public safety. Okay, let's pivot away from catastrophe and look at another amazing digital magic trick. We are sending unbelievable amounts of data over the internet every single second. But how exactly do massive 4K video files or gigantic folders of high-res images just compress into tiny zip folders that we can email in an instant without losing their quality? How is that physically possible? Well, the answer lies in a specialized type of graph called a tree, specifically a massive breakthrough from 1952 known as Huffman coding. Get this, it was actually created by a student, David A. Huffman, who was just asked to design the most efficient method for data compression. His brilliant idea was to use an optimal binary tree structure. It basically assigns much shorter codes to the most frequently used characters in a file and longer codes to the rare ones. This simple but incredibly elegant logic reduced storage requirements forever. Every single time you open a zip file, look at a JPEG, or stream an MP3, you are benefiting directly from Huffman's tree. And discrete structures do a lot more than just compress our data. They are our invisible safety net. Think about logging into your bank account. That is number theory at work, using massive prime numbers to lock out hackers. Behind the scenes, modular arithmetic is hashing your passwords, while Boolean logic is acting as the absolute strict gatekeeper for your digital payments. And hey, if you're transmitting files over some spotty, corrupted Wi-Fi or receiving data from a noisy deep space satellite, advanced algebraic structures, things like groups, rings, and fields, they step in to create mathematical error-correcting codes to ensure your data survives the trip completely intact. So when you take all these abstract units and map them to the real world, the career implications are just undeniable. Mastering logic and trees, that isn't just textbook theory. It's the direct path to building AI and designing massive back-end databases. Combinatorics and number theory form the absolute bedrock of modern data science and cybersecurity. And graph theory, as we've already seen, is absolutely essential if you want to get into network engineering or routing applications. You simply cannot build the tech of tomorrow without speaking this mathematical language today. Which brings us to a really powerful concluding thought for this explainer. Great software is not built with programming alone. It requires strong mathematical thinking. You can be a fantastic lightning-fast coder, but if you're trying to build a navigation app and you completely ignore graph theory, your users are going to be stuck in traffic, for sure. True innovation requires going way beyond just typing syntax. It requires mastering the underlying logic that governs how information itself actually works. So let's wrap this up with a quick challenge just to test what we've covered today. Which real-world application mainly uses graph theory? Is it A, word processing, B, Google Maps route navigation, C, a calculator, or D, image editing? If you were paying attention back when we talked about Euler's bridges, you know the answer is absolutely B, route navigation. But honestly, solving today's puzzles is really just the beginning. As we push further into the era of quantum computing and neural networks that almost defy human comprehension, how are these ancient mathematical structures going to need to evolve? Will the discrete math of tomorrow look anything like the logic we use today? Thank you so much for joining me on this explainer, and I'll leave you to ponder that one.